Section 2.6 deals with differentials. So recall, the difference quotient is that f of x plus h minus f of x, and we said all over h, but we can think of it just as we did for average rate of change, which is 1x minus the other x. Now, incremental notation helps us to interpret the numerator and the denominator of the difference quotient separately. So it helps us look at the change in y over the change in x separately. So let's look at an example of what's going on here. So let's say we're given that f of x is equal to x squared. If x changes from 2 to 2.1, then the increment of x, or the change in x, is 0.1 units. And y is going to change. Well, if x is 2, y is 4. And if x is 2.1, y is 4.41. So the increment of y, or the change in y, is going to be equal to 0.41 units. So my y's change 0.41 units, and my x change 0.2 units. If I'm looking at f of x equals x squared from 2 to 2.1. So, on a graph for y equal f of x, so just in general for any y equal f of x, if you have two x values, x sub 1 and x sub 2, the change in x is going to be the difference between those two values. And the change in y is going to be different of the two y values. But instead of calling this point here y sub 1 and this point here y sub 2, we know that we can call it f of x sub 1 and f of x sub 2, or the function's value of x sub 1 and the function's value of x sub 2. So delta y, or the change in y, can be the change in f of x sub 2 minus f of x sub 1. Now, if we go back up to this line here, delta x is equal to x sub 2 minus x sub 1, and we were to solve that for x sub 2, so we would add x sub 1 to both sides, we end up with x sub 2 is equal to x sub 1 plus delta x. So the incremental for delta y, instead of it being f of x sub 2 minus f of x sub 1, we can see it as f of x sub 1 plus delta x minus f of x sub 1. Now this is very similar, and over here I've kind of pointed out it to you that x sub 2 is the same as x sub 1 plus delta x, and that delta y over here is the same as f of x sub 1 plus delta x minus f of x. So we've looked at all of that, but this should look really similar. It's no different to what we saw before with our difference quotient, which was our f of x plus h minus f of x all over x plus h minus x, right? It's no different from that. So the incremental delta y is always going to be the change in your y's. The incremental delta x is always going to be the change in your x's. So let's look at an example where we're applying some of this. Example 1. Given that y equal f of x is equal to 2x cubed, find delta x, delta y, and delta y over delta x, which is our slope, right? Given that x sub 1 is equal to 1 and x sub 2 is equal to 3. So, part A, find delta x. Well, delta x is always going to equal x sub 2 minus x sub 1. Well, x sub 2 is 3, x sub 1 is given as 1, so my delta x is equal to 2 in this case. Second thing I'm asked to find is delta y. Well, delta y is equal to the function's value at x sub 2 minus the function's value at x sub 1. So in order to find delta y, I need to figure out what happens to the function when I plug in 3 and what happens to the function when I plug in 1. So f of x sub 2, which is the same as f of 3, because that's what x sub 2 is going to be, well, that just means plug in a 3 everywhere there's an x in your function. So it would be 2 times 3 cubed. And 2 times 3 cubed, 2 times 27 is 54. Then f of x sub 1, well remember f of x sub 1 was given as 1, so f of 1 is going to be, again we're just going to plug in a 1 in place of the x there in the function. So 2 times 1 cubed, and 2 times 1 cubed is equal to 2. So then my delta y is going to equal 54 minus 2, which is 52. So delta x was equal to 2, and delta y is equal to 52. And that was part B. Part C is just asking you to find delta y over delta x. Well, delta y, we already found that to be 52. Delta x we found to be 2. So delta y over delta x, 52 over 2, is equal to 26. All right, let's look at number 2. For f of x equals 2x cubed, find f of x sub 1 plus delta x minus f of x all over delta x, given that x sub 1 is equal to 1 and delta x is equal to 2. Okay, so what I need to do is find f of x plus delta x and f of x sub 1 as well. So f of, well, x sub 1 is given as 1 plus, and delta x is given as 2. Well, that's the same as f of 3. And f of 3 says, hey, everywhere there's an x in your function, instead of writing that x, write a 3. So we get 2 times 3 cubed. And we already figured it out, because this is really the same problem as above, that equals 54. And then I need to figure out what in the world is f of x sub 1. Well, f of x sub 1 was given as 1. F of 1 is just going to be that 2 times 1 cubed. Well, 2 times 1 cubed is equal to 2. So, if I want to find f of x sub 1 plus delta x minus f of x sub 1 all over delta x, well, that would be 54 minus 2, because 54 is my f of x plus delta x sub 1 plus delta x, and 2 is my f of x sub 1 all over, and delta x is given 2. So I end up with 52 over 2, which is 26. And that's the same answer that we got for part C. Why is it the same answer? Because this here is just equal to delta y. So delta y and everything else in our problem was the same as it was for example 1. So delta y is just how much does my y change. Delta x is how much is my x changing. So differentials. We start this off by showing the increments and then talking about differentials. So if we have small increments of x, so if the movement we have away from x is pretty small, then delta y over delta x should be pretty close to what the derivative is. So delta y over delta x should be really close to the derivative is. Okay, let's talk about what this represents real quick before we move on. Now we know that f prime of x, this thing over here, this represents the slope of the tangent line. And we know that delta y over delta x also represents the slope. So what this is saying is, hey look, if you've got a graph of any kind of function, and you want to find the slope of, let's say, this line right here, well, if you don't really move too far away from x, right? If you choose 2 points and do it this way and don't move too far away from x, the slope of the lines is going to be pretty similar. That's what that's saying. As long as you don't really move too far away from x, the derivative evaluated at a point and the slope that you obtain using the average rate of change should be really close to each other. Thus, if we say that, then delta y over delta x would equal f prime of x. If I solve it for delta y is always going to equal f prime of x times delta x. If y equal f of x is a differentiable function, then the differential dy, or df in some cases, is defined as follows. dy is equal to f prime of x times dx. Same thing that's written right there. Or df is equal to f prime of x times dx. And this is where the change in x or dx and delta x are equal to each other. So dy, or the differential, is an approximation of the actual change in y. So the differential dy is an approximation of the actual change in y, which is your delta y. So delta y is the actual change in y, dy is the approximate change in y. And the thing is that the approximate change in y should be really close to the actual change if the movement away from x is not very large. All right, let's look at some examples when we're finding differentials. Example 3. Find dy and delta y for each function for the indicated values. So I get that y is equal to f of x, which is equal to 2x cubed plus x. We're given that x is equal to 1, and that dx, which is equal to delta x, is equal to negative 0.5. So let's start with finding delta y first, because we've had more experience with that. Recall from above, delta y was equal to f of x sub 1 plus delta x minus f of x sub 1. Well, x sub 1 in this case is 1. So I need to figure out, okay, what is f of 1 plus, well, what's delta x? Well, delta x is given as negative 0.5. And I'm going to subtract that off of f of, remember, x sub 1 is just 1. So I need to figure out 1 minus 0.5 is what is f of 0.5 and what is f of 1. Put it all together and I find the actual change in y. So I need to figure out what these two things are. So on the side here, well, f of 0.5, again, all we need to do is plug it into our given function. So f of 0.5 is going to be whatever 2 times 0.5 cubed plus 0.5 is, because we need to plug it into every x in our given function. So just grabbing a calculator to figure that out. So 2 times 0.5 to the third plus 0.5 gives us 0.75. So this is going to equal 0.75. Okay, well, what is f of 1? Well, that's going to be whatever 2 times 1 cubed plus 1 is. Well, 2 times 1 cubed plus 1, we don't need a calculator for that. That's just going to equal 3. So f of 1 is equal to 3. Which means for us that delta y is going to equal 0.75 minus 3. And 0.75 minus 3 is going to be negative 2.25. So the actual change in y is negative 2.25. Well, what about the differential? What is dy equal to? So dy is the approximate. Well, dy is equal to, if you look up here, it's equal to f prime of x times dx. So in order to figure out what dy is, I first need to figure out what the derivative of this function is. So if this is my given function, the derivative f prime of x would equal, well, 2 times 3 is 6, x 1 power less, so 3 minus 2 is squared, plus, well, the derivative of x is x to the 0, right? Because the exponent on there, and I told you guys x to the 0 is equal to 1. So f prime of x is equal to 6x squared plus 1. So then, what I need to do is I need to say that dy is equal to f prime of x, which is my 6x squared plus 1, times my dx. Well, what is that equal to? Well, what is the value of x that I'm looking at? Well, the value of x that I was given was x equal 1. So now I want to evaluate dy when x is equal to 1. And typically, the way that we write this is we write dy a bar down and put x equal 1, knowing that what we're doing is plugging in a 1 in place of all the x's in our given equation here. So we're going to plug in a 1 in place of the x there. So we're going to say 6 times 1 squared plus 1 times dx. Well, dx was also given. What is dx equal to? Well, dx was given to be, remember, dx was equal to delta x, which is equal to negative 0.5. So dx is equal to negative 0.5. So if we evaluate this, and we can use a calculator for it. So we have 6 times 1 squared plus 1. And that whole entire thing gets multiplied by negative 0.5. We end up with negative 3.5. Negative 3.5. So the approximate change in y is negative 3.5. The actual change in y is negative 3.5. And those two are not at all really close to each other. Now, why? Why is it that they're not that close to each other? Well, if you're moving a half unit away from something, in terms of mathematics or engineering or anything like that, that's a pretty big movement, a significant change, right? If you're moving maybe 0.1 units away or 0.01, that's not very far movement. But 0.5 is a big movement, and especially if you have a polynomial like this that is growing pretty fast. So here, our delta y is negative 2.25, and our dy was negative 3.5.